This meeting is being recorded.
In this next video from chapter 16 on acid-base equilibria, we're going to take a look at sample exercise 14. And this question is about a polyprotic acid, specifically oxalic acid, and we're given that molecular formula here. We're told that we can reference table 16.3 for the Ka1 and Ka2, but I've provided them for us over here, so we don't have to venture away from our page, because you might have noticed there's a lot to do here. We're going to need the quadratic formula to solve for our x once we create our ICE table for this problem. And the reason that we have to do this is, I've alluded to this in the past, that we may need the quadratic formula, but our K values for previous acids, usually monoprotic that we've looked at, they've been much smaller than this, maybe 2 or 3 magnitudes smaller. So this is to the -2 power here, this 5.9 times 10 to the -2. So what that means is that at our equilibrium concentration, that X value is no longer negligible. And I'll reference this again when we get to that point in our calculation. So let's get started here since we have a lot to do. We have our oxalic acid. We're going to add this to water. We get our dissociation here, so we know we're going to get hydronium because it's an acid, and then we're going to get our first product here, C2O4 negative. So we have our equation given, and then we have to create our first ICE table here. Remember, with multiple K values, multiple ionizations or dissociations, we're going to have multiple ICE tables involved as well. So our initial concentration given above is that 0.020 molar. We can cancel out our water column, and then we assume that we don't have any of our product to start. What's our change? From the balanced chemical equation that I have drawn for you here, we see that we have 1 to 1 to 1, so all of our x's will be like so with a coefficient of 1. Then we're going to add these together to get our equilibrium concentration here. So we have 0.020 minus x, and then we have x and x. So we'll use this quadratic formula and quadratic form a little later, but for now we're going to plug into our Ka expression, and we know that that's going to be our products, and then, just negative for now. And then we have over our reactant, so our oxalic acid, so H2C2O4. But again, we know that due to our acid dissociating maybe a little bit more than 5% with this type of Ka here, we're going to need to account for this X here at our equilibrium. So that's why it's not negligible. So we're going to need to solve for X. So let's set our equation here. We're going to have X squared over our 0.020 minus x equal to our first Ka value, that 5.9 times 10 to the -2. All right, so we're going to have to rearrange this equation here and get it into quadratic form. What is quadratic form? If you ask, it's this right up here. So let's get started. We're going to multiply both sides by 0.20 minus x. So I'm just going to cancel this out here. I'm going to multiply it over here. Let's rearrange this a little bit here. So I'm going to put x squared. That's going to be equal to, now I can multiply these two terms together, and I'm going to get 0.00118, and then we're going to have minus 5.9 times 10 to the -2 x when we multiply this times x. So we're almost there. We're almost in quadratic form. Now I'm going to have my x squared. Now I'm going to add plus 5.9 times 10 to the -2x to each side. And then we're going to subtract this value, 0.00118, from each side. All right, so now we have this equal to 0. So this is in quadratic form. Let's pick out my A, B, and C value. So my A value, that's going to be 1. Right, we have no coefficient there, so we assume it to be 1. My B is going to be this guy here, positive 5.9 times 10 to the negative 2. And then my C value is going to be this term, including the negative. So if you'd like to solve this by hand, I can show you how to do that fairly quickly. But there's also, at the top of this page, there's a quadratic calculator link. You can go to this website, calculatorsoup.com, and just kind of plug in your A, B, and C. Make sure you get it in the right notation and positive or negative, and you should generate an X value. So let's see if we were to solve this by hand. We would have our B value. I'm going to write this in a slightly different form. So it's going to be negative B, and then plus or minus the square root, again, of my B squared, so 0.059 squared, minus 4 times A times my C. That's a negative, right? 0.00118. So we have our denominator as well, so that's over 2 times 1. So we'll just divide by 2. So what we see here is if we were to simplify our terms, we're going to get x equals negative 0.059 plus or minus all this term here over 2. So only one of these terms after we solve will give us a positive answer. So I will trust you to plug everything into your calculator, and you should get an X value to 0.0158. And again, only the positive answer would make sense here. So we're going to keep moving. We're going to create our second ICE table, and we're going to start with this value here. So let me clear us some space. All right, so now our second ICE table, we're going to start with our products, right, as our reactants here instead. So we're going to have, or product rather, this guy here, HC2O4 negative plus water, and then we're going to have that second ionization here. So that's going to be hydronium, and then our C2O4, 2 negative now. And in our question, we're asked to solve for that as well. So we'll have to solve for one more X here. So let's get our ICE table in, and we have that 0.0158 here. This is not needed. We're going to start with this 0.0158 here. And then this would be 0. So my change is going to be the same, minus x, plus x, plus x. So here we get x and x. Here we get 0.0158 minus x. So let's see what happens when we set this equal to our second Ka. So just to refresh our memory, that is 6.4 to the negative 5. So we're going to set this equal to x squared over our 0.0158, our initial minus the change here. And let's take a look at what happens. So our x values, actually for here, this would be x times, and I didn't add this correctly, so 0.0158 plus x will be here. Without this, the magic doesn't happen. So these terms actually cancel out, and we see that our x for this is going to be equal to our second Ka value. So we have one of our answers here. Our C2O4 to negative concentration will be equal to our second Ka value. So that's complete. And then now we have to add our change in x here, our change in x over here to our starting value to determine our hydronium ion concentration. But I'll give you a hint. When we add these values together, the x here is so small that it won't change anything. So we're just going to plug in this guy here, 0.0158 to find pH, we're going to do negative log of that. So negative log of 0.0158 gives us a final pH, and I'm going to write it over here, of approximately 1.80.